What you're looking at now is a quick reference for antiderivatives. The list that you see is a very helpful tool. So in the future, as you work on assignments where you are asked to find the antiderivative of various functions, this list is going to greatly help you. I suggest that maybe you print this out or perhaps just handwrite it so you have a copy of this available. Whatever works for you, but just have this available so as you go through different problems trying to find the antiderivatives, this list will make your work a lot easier. Just to give you an idea, I'm going to illustrate a couple of these for you. The first one I'm going to look at is actually right here, the antiderivative of k dx. And in the list, of course, we tell you that the answer is going to be kx plus c. So let's look at that a little more thoroughly so you get an idea of how to use this list and how helpful it is. So keep in mind, first of all, antiderivatives are the opposite of finding the derivative. So we're asking if we take the derivative of kx plus c, we're going to get k dx. So antiderivatives would start with this and say, if this is the answer to a derivative, what was the original function? To make this even more clear, I'm going to make this concrete by defining k. I picked a random integer. In this case, k is equal to negative 21. So we have the antiderivative of negative 21 dx is equal to negative 21x plus c. That's the answer. So we have our answer right here. To go a step further, normally you wouldn't be asked to do this, but I just want to illustrate a point. I'm going to find the derivative of negative 21x plus c to show you that it takes us back to what our antiderivative was. So if I differentiate negative 21x plus c, I have that dy dx is equal to negative 21. So the derivative of negative 21x is negative 21. The derivative of c, or the derivative of any constant, is 0. And if I multiply both sides by dx, we have negative 21 dx, which is what we started with originally up here. So again, that check is not a normal part of the process, but I just wanted to throw that in to help illustrate how derivatives and antiderivatives are inverse operations. On our quick reference for antiderivatives, we're going to take a look at another example to see how we can use this list to help us find antiderivatives. And the one I'm going to consider is right here, the antiderivative of k to the x to the n power. So this is saying that there was a function, I took the derivative of it, and the answer is kx to the n. And we can see here that the answer is going to be k over n plus 1 times x to the n plus 1 power plus c. And we have this little notation here that n cannot equal negative 1, and that would be because if n is equal to negative 1, we have 0 in the denominator. Let's make this concrete by taking a look at an example where I define what k and n are. So in this case, I'm going to let k equal 1 and n equal positive 4. So the problem will look like this. The antiderivative of x to the 4th power dx. So we took the derivative of a function. This was what we ended up with. So what was that original function? Well, to find out, what I do is I add 1 to 4, gives me x to the 4 plus 1 power, and the denominator would be 4 plus 1. So our final answer would be x to the 5th over 5 plus c. You can also rewrite that as 1/5 x to the 5th plus c. And if you want to do a little extra work on your own, you can differentiate this function and see if you end up with x to the 4th up here. I'm going to stay with this example and take a look at another variation of this. Now keep in mind, antiderivatives reverse the derivative process. So when you're finding the derivative, you multiply the coefficient times the exponent and then subtract 1 from the exponent. So the antiderivative would be you add 1 to the exponent and divide by the exponent plus 1. That's where we get this n plus 1 over here. So let's say k is equal to 6 and n is equal to 2. So we want to find the antiderivative of 6x squared dx. And we do that by adding 1 to the exponent. So that's why I have 6x to the 2 plus 1 power. And then I introduce a denominator, which is also n plus 1, or in this specific case, it's 2 plus 1. And we don't forget our constant of integration. Simplifying this, we have 6x cubed divided by 3 plus c, which gives us 2x cubed plus c. And if you'd like to take a little time on your own, differentiate 2x cubed plus c, and you should get 6x squared. We've been looking at this one particular case right here where we're finding antiderivative of k times x to the n power. And we've said that we have this special notation that n cannot equal -1. Let's see what happens if n does equal -1. Let's explore that a little bit. So if n is equal to -1, we're going to let k equal 1 just to make our work simple. So we have the antiderivative of x to the -1 power dx, and we add 1, just going through the regular process, gives us x to the 0 power over 0 plus c. And we have 0 in the denominator. Okay, that's a travesty in the world of math. You don't do that. You don't have 0 in the denominator. So obviously there's a problem, okay? And when x is equal to, when n is equal to -1, we actually use a different, I'm grabbing the wrong one. We use a different identity. We use a different reference. We're going to use the integral of 1 over x dx is equal to the natural log of the absolute value of x plus c. So if we have x to the -1 power, or another way to write it is 1 over x, and we're finding the antiderivative of 1 over x dx, that's going to equal the natural log of the absolute value of x plus c. Finally, I'm going to take a look at a trigonometric trig function. So we're going to take a look at this one right here, the antiderivative of cosine x dx, and it tells us that it's equal to sine x plus c. So in a future problem, if you're asked to find the antiderivative of cosine x dx, the answer is going to be sine x plus c. I'm going to go a step further and just kind of give you some background as to why this is and how this works. So we know that the derivative of sine is cosine. So if I start out with y is equal to the sine of x plus 3, dy dx is going to equal the cosine of x. Remember, the derivative of 3 is 0. If I multiply both sides by dx, that gives us dy is equal to cosine x dx. So when you're asked to find the antiderivative of cosine, it's kind of reversing the process. You took the derivative of a function, you got cosine x dx. What was that original function? So since we know the derivative of sine is cosine, the antiderivative would be sine x plus c. Again, if I didn't know the original function or didn't have any other information, I wouldn't know that c was equal to 3, so I just leave it in the general term. If I was given some information, I would be able to solve for c specifically. But in this case, we're just going to leave it plus c.